primary equation. What I want to optimize secondary equation is to be substituted into the primary equation. Some other constraint that I don't need to find the maximum or minimum value. We're going to use the derivative to find the min or maximum value of our primary equation. We're back from before winter break. Talking about minimums or maximums. What is the value of the derivative at a minimum or maximum point? The value of the derivative has to be what? 0. At the top or bottom, the derivative has to be 0 because that's where it changes from increasing to decreasing or decreasing to increasing, vice versa. So once you have your two equations right, you want to find the derivative of the primary equation and set it equal to 0, because that's what I'm trying to optimize. That's what I'm trying to find the minimum or maximum value of. Usually that primary equation is written in more than one variable, written in terms of more than one variable. So I have to substitute the secondary equation into the primary equation before I can take the derivative of it. The secondary equation is substituted into the primary equation to reduce it to be in terms of, I have it in terms of variable, I'm trying to find the optimal value, the minimum or maximum value. So therefore, I need to find where the derivative is equal to 0. To find the minimum or maximum or something. So here's our just first beginning basic problem. I want to find two positive numbers whose product is 48, and the sum of those two numbers is a minimum. So let's write our system of constraints. Let's write the primary and secondary equation up in this. I want to find two positive numbers and whose sum is the minimum. Let's let x and y be two positive numbers. What I want to optimize. I want all of these to be a minimum. So my primary equation is going to be x plus y, the sum of my two numbers, equal to some, let's just call it S for sum, or M for minimum, whatever you want to do. I know that x plus y is going to have some sum. That's my primary equation, because that's going to involve the quantity, the sum that I want to make as small as possible using the derivative. What else do I know about this pair of numbers? Okay, so that's going to be the secondary equation. That's some other constraint that is not a part of the optimal value. I'm not trying to make the product a minimum or maximum. I'm trying to make the sum a minimum. I just also know that the product needs to be 48. So x times y the minimum sum of these two numbers. We've got our secondary equation. That's some other given constraint in our problem. Now, I want to find the minimum sum of these two numbers. So I need to take the derivative and set it equal to 0. Find the critical numbers that make this sum as small as possible. Now, right now, my equation written in terms of two variables, in terms of x and y. I want to get it reduced down in terms of one variable. So let's use our secondary to put our primary equation back into terms of one variable. I need to solve this secondary equation for either x or y. Doesn't really matter. Give me one you want to solve for. X, all right, so let's solve for x. I'll need to divide each side by y. If x times y equals 48, to solve for x, I divide each side by y. So x equals 48 divided by y. I can substitute that into the primary equation to put it in terms of only one variable, to put it specifically in terms of x. I'm sorry, substitute for x to put it in terms of y. Now let's take the derivative. This is what I want to find the minimum value of, what I want to make as small as possible. So I'm going to find the derivative and set it equal to 0. Find the critical numbers. Really, let's write this as 48y to the negative first. What's the derivative of 48y to the negative first? Use power rule. Right, so negative 48 over y squared. Equal to, let's just call that s prime for the derivative. I want to find the critical, what do I have to set this equal to? What would the derivative be equal to where this quantity is either the minimum or the maximum, as big or as small as possible? 0. So set this equation equal to 0. Negative 48 over y squared plus 1 equals 0. Now I just need to solve for y. We subtract 1. What can I do next? Just going to get rid of the negatives here. Get rid of the negative on both sides to make it y squared equals 48 divided by y squared. What's next? Square root. So y equals the square root of 48. I simplify that, let's see, 16 times 3, but the square root of 16 is 4. So one number is 4 square root of 3. I have to find. I know that y equals 4 square root of 3. Am I done? What else do I have to solve for? X. I need the other number. One number is 4 square root of 3. What does the other number have to be? Which equation would be helpful if I want to solve for x, given the value of y? But it's already solved for x right here, right? Secondary equation, solve for x. If I know x equals 48 by 3, let's just put it to solve for x. X equals 48 divided by 4 square root of 3. You take the value of y and use it to find x. Let's see if I can simplify this value. Multiply by an extra square root of 3 to top and bottom. It's going to give me 48 square root of 3 divided by, what's the square root of 3 times the square root of 3? 3. This makes 3 times the other 4 out in front. 3 times 4 is another. Now I can divide the top and bottom by 12. 48 square root of 3 divided by 12 is also 4 square root of 3. The two numbers, x and y, are both 4 square root of 3. Their sum, and their product is 448. 4 square root of 3 times 4 square root of 3. Any other pair of numbers that has a product of 48 would have a value, a sum, greater than 8 square root of 3. Let's try another one. I've got this question kind of detailed up on the television screen here. Let me share my screen so everyone can see. This is going to be about land area. The 3 pens example here. All right, so in yellow, it says that a farmer has 1,200 feet of fencing and needs to create a regular enclosure with 3 pens as shown above. So I basically got a rectangle subdivided into 3 different portions. To create 3 different equally sized pens. What should the dimensions of the total enclosure be to create a maximum area? I want to fence in as much pasture, as much land as possible. I've got 1,200 of fencing to use. So what are the dimensions of the enclosure so that the total area is a maximum, as large as possible? Aren't there lots of different ways to create this? If I move this blue dot, the perimeter is still 1,200 feet of fencing. I'm still always using 1,200 feet of fencing. I could make a lot of different types of areas for the enclosure, right? Which one of these produces the largest such area? The largest enclosed, that's what we have to find. Let's write a primary and secondary equation based off of what we know. Whatever I want to find the largest, smallest, whatever I want to find the minimum or maximum. The secondary equation is whatever I'm not going to optimize. Some other constraint given the question. Now I have to substitute this into the primary equation to put the primary equation back into terms of only one variable before I take the derivative and solve for my critical value. Strengths of equation given this setup. What variable should I use? It doesn't matter. X. What do you want to use for this distance? Y, okay? So let's let X be this portion of the total width. This is the height. I need a primary equation of constraints. want to find the optimal value of? What do I want to have be the largest or smallest in this? The area. So given x and y, what expression would denote the area? X times y would only be one of the 3 pens, though, Shay. If this distance is x, what's that distance in terms of x? 3x. 3x. So what expression is the area again? 3x times y. The area is 3x times y. Okay. That's what I want to find the largest value. What is the largest value that the area can take on, given this system of constraints? What's that optimal value? I'm also given some other constraints, some other limiting equation here. What else do I know?
The total area is 1,200 feet.
Not the total area, the total. I already got the area put together. What else do I know? I've got how much fencing? 1,200. So I need to use 1,200 feet. This, all the different sides that subdivide them. We start with the x's. 6x. Where's the 6x coming from?
Well, there's 3 areas of x on one side.
There's 3 lengths of x per top and bottom. So that would be 6x. How about from length? How many lengths y are there to subdivide this into 3 pens? So here's our system of constraints. Notice that I need to take the derivative of the primary equation because that's what I want to either find the minimum or maximum value of, but the primary equation is written in terms of 2 variables, both x and y. So that's why I need to substitute the secondary equation into the primary equation before I find the critical values. So pick a variable. It doesn't much matter. What do you want to solve the secondary equation for? Either x or y. Okay, let's solve for x. Get x by itself. You could just easily solve for y. Let's solve for x. So let's subtract 4y from either side. 6x equals 1,200 minus 4y. What do you do next? Divide by 6. So let's see. That would be x equals 1,200 divided by 6 is 200. 4 divided by 6 would be 2/3. Now that I know that x equals 200 minus 2/3 y, what do I do with that? Right, because that's going to allow me to write my primary equation specifically in terms of y, so that it's easier to take the derivative of. So that it's only in terms of one variable, and therefore easier to find the critical numbers of. So let's see what we got. A equals, the area equals, in terms of y, 3 times quantity 200 minus 2/3 y times y. X, y, 3 times substituted in for x. 200 minus 2/3 y. Question so far? Let's take everything times 3y. So 3y times 200, 600y. What's 3 times 2/3? What's 2/3 of 3? 2. So this would be 2y squared minus 2y squared. So only in terms of y, there's our expression for the area. What do I want to do to the area? I need to find its optimal value. I need to make it as big or as small as possible. In this case, as big as possible. How do I do that? How do I use the derivative to do that? Zero. Remember, there's a minimum or maximum. The derivative has to be 0. That's where it changes direction. So let's take the derivative, a prime, equal to, see, what is the derivative of 600y? 100, 2y squared, the derivative would be 4y. We'll set this equal to 0. See here, 600 equals 4y, and then divide by 4. 600 divided by 4. So 4 divides into 400, 100 times. 200 more left over. Is that 150? Y is 150 feet. Am I done? All I've got is the width. Am I done? What do I have to solve for next? If I know what y is, how could I use y to find x? What do I do with my y value now? Yeah, let's plug it into here. Here's an equation that represents x in terms of y. I know y is 150, so back substituted to solve for x. So x equals 200 minus 2/3 is 150. One third of 150 is 50, so 2/3 would be 100. 200 minus 100 is 100 feet. Now that I know x and y, what are the total dimensions of this? What's the total length and the total width? Total length would be how long? 300 by 150. 100 feet. By 150. That would produce the pen that encloses the largest amount of area. I'm thinking about how this is set up here. That's not much area. That's not much area. Isn't it kind of maybe right here in the middle? I think that'd be about the largest area given this amount of fencing. Questions here? Okay. Question or a little, but they're both solved using a system of equations in terms of a primary equation